In the last lecture, we gave motivation for why understanding eigenvectors and eigenvalues could be handy for calculating a matrix power times a vector. What I want to encourage you to do is to see beyond the algebraic to the geometric, and that means thinking in terms of transformations, not just calculations. Matrix powers can arise naturally in applications where there's some repeated action of a transformation on quantities of interest. For instance, we looked at population dynamics of foxes and rabbits and set up a simple mathematical model. There, the vector that was of interest was the population of foxes and rabbits. The populations of foxes and rabbits at time n gives rise through the model to the population of foxes and rabbits at time n plus 1. So there's a repeated action of a transformation taking the time n populations to the time n plus 1 populations. And the transformation defined by our model is linear. So let me emphasize, this is such an important idea, to think of transformations rather than just thinking about calculations. The word transformation conveys the idea that a whole set of inputs are getting changed simultaneously to a bunch of outputs. So the calculations in each instance are related by some larger function, in this case a linear transformation, represented by matrix multiplication. In some instances, a transformation we are interested in may not be linear, but if it's approximately linear, then we can begin to understand it using the tools of linear algebra. What we are going to see in this lecture is that every matrix, which, as you recall, represents a linear transformation, has associated with it eigenvectors and eigenvalues. And these actually represent important geometric features of the transformation. They are special vectors and values that have some meaning. This demonstrates one of our themes, that linear algebra helps reveal hidden structures. These hidden structures of eigenvectors and eigenvalues, in some sense, characterize the matrix. In fact, the German prefix eigen can be translated self or own or characteristic, and it suggests that these eigenvectors and eigenvalues characterize the matrix in some way. And these structures are actually quite natural. To convince you of the naturalness of looking at eigenvectors and eigenvalues, let me convince you that nature chooses to look at these things. And I'll do this by giving you just a sense of how the quantum mechanical world works, which governs physics on a subatomic scale. I've alluded to the fact that the concept of vectors is more general than just being finite collections of numbers. The important idea of a vector space is that it is a collection of objects for which it makes sense to take linear combinations. In physics, the possible states of a quantum mechanical system is called the state space, an idea that turns out to be modeled well by what's called a complex Hilbert space. It's not so important for our purposes that you know what that means, except to point out that this is a vector space. There's a notion of a dot product, which gives a notion of angle and length, and that scalars come from the complex numbers. The complex numbers are numbers of the form a plus bi, where a and b are real numbers, and I is a symbol with the property that I squared is -1. The complex numbers is basically a number field in which square roots of negative numbers exist. And a complex vector space is one in which linear combinations of vectors may have complex coefficients. In this vector space, the vectors are the states of the system. And the strange part of quantum mechanics is that the state of the system could be in what's called a superposition of other states, basically a linear combination of states. Thus, a given state could be a linear combination of basis states. And usually, you don't know much about the state of a system unless you take a measurement. Anything you can measure, like position, momentum, or spin, corresponds to what's called an observable. And in quantum mechanics, an observable is modeled well by what's called a Hermitian linear operator. Again, it's not so important what that means, except that you should think of it as a linear transformation on the state space. So an observable, as a linear operator, has eigenvectors, called eigenstates, and eigenvalues. And when you take a measurement of an observable in quantum mechanics, you actually change the state of the system into one of the eigenstates. And the value of the measurement you observe is the eigenvalue for that eigenstate. So what you see here is that nature naturally chooses eigenstates. Now, I didn't really expect you to understand all that, and there's much more that could be said, but I wanted to give you a glimpse of the cool linear algebra ideas that permeate much of the physics of the subatomic world. Now, we stress the importance of thinking about matrix multiplication as a linear transformation on a vector space rather than some random calculation that you have to do. Because if you understand a transformation, you can comprehend all at once what the transformation does. Let's see if we can unpack that. Recall that if you have a square matrix that's n by n, let's call it A, and you can find a non-zero vector v such that AV equals a multiple of v, let's say lambda v, then we say lambda is an eigenvalue of A and v is an eigenvector of A corresponding to the eigenvalue lambda. Here the matrix A times the vector v can be thought of as taking a vector and seeing how it behaves under the linear transformation t of x goes to A times x. This takes the entire plane and transforms it by multiplying by A. And how does it change the plane? Well, first of all, we know that the origin goes to the origin. And the basis vectors, red in the diagram, go to the vectors that represent the columns of A. And lines get sent to lines. That means a grid of squares like this gets deformed to a grid of parallelograms like this. And this smiley face gets deformed to this one. And if the winking face is now backwards like this, it suggests that the matrix A has a negative determinant. The absolute value of the determinant is the ratio of the area of the parallelogram to the area of the original square. Comprehending this geometrically, we can now discern where any other point should go. We just figure out where it is on the grid of squares and look for the corresponding point on the grid of parallelograms. But this grid of squares is based on the standard basis vectors, which was a rather arbitrary choice and not really the most natural vectors to look at when trying to understand this transformation. Perhaps better ones to look at would focus on the ones that don't change direction, the so-called eigenvectors. If we could find such vectors, then the grid based on these eigenvectors wouldn't change much under the transformation. It would change scale along these directions, but the grid orientation would stay the same. For instance, if you look at this vector v1, it gets sent to t of v1, which is a multiple of itself. So it is an eigenvector, and the scaling factor is the eigenvalue. The eigenvector nearly doubled in size under this transformation, so we can see the eigenvalue is about 2. And this vector, v2, gets sent to this point, t of v2, pointing in the same direction. So it's an eigenvector. Can you see what the eigenvalue is in this case, approximately? It's smaller than 1 because the vector shrank. The nice thing here is we can see what the transformation is doing to other vectors simply by looking at their components in the eigenvector directions. So this point, which is the sum of v1 and v2, goes to this one, which is the sum of t of v1 plus t of v2. You can easily follow a point by looking at its location on the grid and looking for the corresponding point on the image grid. Since we are fortunate that v1 and v2 form a basis for R2, any vector can be found on this grid. In other words, any vector can be written in terms of v1 and v2. And once you know where the basis vectors go under a linear transformation, you know where every other vector goes just by looking at the image grid. So knowing the eigenvectors and eigenvalues can give us a more natural structure by which to describe the action of a linear transformation. Before we discuss how to actually compute eigenvectors and eigenvalues, let's look at some examples to make sure we understand the definition. For instance, is the vector 2, 5 an eigenvector of the 2 by 2 matrix A with entries 1, 2, 5, and 4? Well, if you take the matrix A and multiply it by 2, 5, you'll get 12, 30. Is that a multiple of 2, 5? Why, yes it is. In fact, it's 6 times 2, 5. This means 6 is an eigenvalue of A, and 2, 5 is an eigenvector of A, corresponding to the eigenvalue 6. One way to think of this is that the matrix A represents a linear transformation, which may expand, shrink, rotate vectors. But for at least this one vector, multiplication by A is very nice. It just scales the vector by the factor 6. There are, however, many other vectors that are eigenvectors corresponding to the eigenvalue 6. For instance, any non-zero multiple of 2, 5 is also an eigenvector with eigenvalue 6, because A times K times 2, 5 is just K times A times 2, 5, which is just K times 6 times 2, 5, which is just 6 times K times 2, 5. Moreover, in this example, the set of all eigenvectors corresponding to 6, together with a zero vector, forms a subspace of R2, and that's called the eigenspace of A corresponding to 6. We can check that the eigenspace satisfies the properties of subspaces. For instance, if two eigenvectors, v and w, with eigenvalue 6, are added together, their sum also has the eigenvalue property. You can see this by checking A times v plus w is AV plus AW, which is 6v plus 6w, which is indeed 6 times v plus w. Now let's look at another vector, 0, 7. Is that an eigenvector of the 2 by 2 matrix A? Turns out, no. You can check this by simply multiplying it out. Take the matrix 1, 2, 5, 4, multiplied by 0, 7, and you'll get 14, 28. This is clearly not a multiple of 0, 7. So 0, 7 is not an eigenvector. So now how do we find eigenvalues and eigenvectors? Well, we'll have to solve the eigenvector equation AV equals lambda v for both lambda and v. And if we move everything to one side, we get AV minus lambda v equals a zero vector. It's tempting at this point to try to factor the v out, but we can't do that because A is a matrix and lambda is a real number. So they don't operate on v in the same way. And the key idea that we mentioned last time is to introduce the identity matrix I as a factor. If we do that, then lambda times I is a square matrix, just like A is a square matrix. Then we can factor the v out. Then the matrix A minus lambda I times the vector v equals a zero vector. Lambda times I is just a matrix with lambdas down the diagonal and zeros everywhere else. Remember, we want to find a non-zero vector v for the eigenvector. But this equation says that v is in the null space of A minus lambda I. The only way that this can happen is if the null space of A minus lambda I is not trivial. by the invertible matrix theorem, that's only true when A minus lambda I is not invertible. But that means that the determinant of A minus lambda I is 0. So we're going to look for a lambda for which this determinant is 0. We now have a way to isolate the process of finding lambda from the process of finding V. So the first part of our method finds eigenvalues by taking the determinant of A minus lambda I to find an expression in lambda that's a polynomial in lambda. In fact, if you think about the definition of the determinant, you can see that this determinant will be an nth degree polynomial for an n by n matrix A. Since we are setting this expression to 0, the eigenvalues will be the roots of this polynomial. And we know how to find roots. You can do it by factoring the polynomial or by a number of other methods. However you do it, what you'll find are the eigenvalues of the matrix A. And by a standard fact about roots of polynomials known as the fundamental theorem of algebra, there will be at most n roots that are either real or complex numbers, and sometimes they'll be repeated with multiplicity. Once you've found the eigenvalues, the next step in the method is to find the eigenvectors associated to each eigenvalue. We do this for each eigenvalue lambda by finding the null space of A minus lambda I. This is called the eigenspace associated to lambda, and we denote it E sub lambda. The eigenvectors are the non-zero vectors in E sub lambda. And to see why, recall that an eigenvector V had to be non-zero, and it had to solve this equation, A minus lambda I times V equals a zero vector. In other words, for a given eigenvalue lambda, an eigenvector V is any non-zero vector in the null space of A minus lambda I. Let's do an example. Suppose we want to find the eigenvectors and eigenvalues of the matrix A with entries 1, 2, 5, and 4. The first thing we do is subtract lambda I from A. In this case, that's the matrix A minus the matrix with entries lambda, 0, 0, and lambda. This yields the matrix A with lambda subtracted off the diagonal entries. So that's the matrix with entries 1 minus lambda, 2, 5, and 4 minus lambda. Now, if you take the determinant of this matrix, you will get 1 minus lambda times 4 minus lambda minus 10, which, if you write it out, factors as lambda plus 1 times lambda minus 6. And if you set this to 0 to find the roots, you will see that lambda is either minus 1 or 6. These are the two eigenvalues of this matrix, 1, 2, 5, 4. Now that we've found the eigenvalues, let's now try to find the eigenspace associated to one of the eigenvalues, in this case 6. This is found by finding the null space of A minus 6i. That means solving A minus 6 times I times a vector V equals a zero vector. The eigenvectors are the non-zero vectors in the null space of A minus 6i. Now we know how to find a null space. We can just form the augmented matrix with A minus 6i on the left and the column vector 0, 0 on the right, and solve like we learned to do before. A minus 6i just looks like the matrix A with 6 subtracted off the diagonal. Then on the left side we have the 2 by 2 matrix, 1 minus 6, 2, 5, and 4 minus 6. And on the right we have zeros. When you simplify this, you see the augmented matrix with rows minus 5, 2, and augmented with 0, and 5 minus 2 augmented with 0. And we notice that the second row is just a multiple of the first. So row reduction simplifies this to just one non-zero row. If the vector v consists of the variables x and y, then this non-zero row represents the equation minus 5x plus 2y equals 0. And we see that y is the free variable. Now we express x and y in terms of the free variable y. Clearly, y equals y, and x can be put in terms of y using the equation minus 5x plus 2y equals 0. And we find x equals 2/5 times y. So the vector xy equals y times the vector 2/5 1, where y can be freely chosen. Then any multiple of 2/5 1 is an eigenvector of A with eigenvalue 6. In particular, 2, 5 is an eigenvector of the matrix A. What about the eigenspace associated to the eigenvalue minus 1? Well, in this case, the matrix A minus lambda I becomes A minus minus 1 times I. And we want the null space of this matrix. Once again, we can solve this by augmenting A minus minus I with a column of zeros. This gives the augmented matrix with rows 2 and 2 and 5 and 5 on the left, and zeros on the right. The second row turns out to be a multiple of the first, so it can be row reduced to a row of zeros. Again, this shouldn't surprise us, because if the matrix A minus minus I is going to have a non-trivial null space, it better not be invertible. So its rank should be less than 2, so it better have a row of zeros when it is reduced. At this point, we are in row echelon form, and we see that 2x plus 2y equals 0 is a relationship between x and y. Or in other words, x equals minus y. When we try to write all variables in terms of the free variable y, we see that x equals minus y and y equals y. So then, the vector xy equals y times the vector minus 1, 1, where y can be freely chosen. This minus 1 eigenspace is all non-zero multiples of minus 1, 1. So minus 1, 1 is an eigenvector of A, as is any multiple. We can check our work by checking to see if the eigenvector equation holds, to see if A times minus 1, 1 equals minus 1 times minus 1, 1. Now, if we take A times minus 1, 1, we get 1 minus 1. And this is indeed minus 1 times the vector minus 1, 1. You can also check that any multiple of minus 1, 1, such as minus 2, 2, is also an eigenvector. Just try taking A times minus 2, 2, and you'll see you'll get minus 1 times minus 2, 2. Now let's look at what's going on geometrically. What is multiplication by A doing to the entire plane? Well, it is taking the eigenspace E6 and stretching it by a factor of 6. The direction of any vector along that line doesn't change, but its magnitude gets multiplied by 6. The origin stays fixed, but anything along the line gets stretched by 6. So if you follow this star in the diagram, it goes, under the transformation, to this dot. Similarly, every vector in the eigenspace E sub minus 1 gets multiplied by minus 1. The net effect of this is to flip the eigenspace about the origin. So this star goes to this dot. And what is happening to any vector that isn't in one of the eigenspaces? Well, in this case, we can write everything that's not in an eigenspace in terms of things that are in E sub minus 1 and E sub 6. So we can figure out where this star goes. As a vector, it is the sum of this star and this star. So under the transformation, it goes to this dot, which is the sum of this dot and this dot. So you can see in this instance that we can easily understand the action of the linear transformation by knowing its eigenvectors and eigenvalues. Recall from the last lecture, we saw a couple instances in which it was useful to raise a matrix to a very high power and apply it to a given vector. In the population dynamics of foxes and rabbits, and analyzing web page rankings. We'll return to those applications soon, but notice that if we wanted to take the matrix A in our example and compute its effect on the eigenvectors we found, it would be very easy. For instance, what if we wanted to find a to the 50th power times the vector 2, 5? Well, since 2, 5 is an eigenvector with eigenvalue 6, the matrix A acts just like multiplication by the number 6. So the answer is just 6 to the 50th power times the vector 2, 5. And we're done. And if we wanted to find a to the 50th power times the vector -2, 2, that would be easy to do as well, because -2, 2, from our earlier work, we recognize it as an eigenvector with eigenvalue -1. So this is just -1 to the 50th power times -2, 2. But that is just -2, 2. That was easy. Okay, time for a more interesting question. What if we wanted a to the 50th times the vector 0, 7? Well, 0, 7 is not an eigenvector of our matrix. In fact, we already checked that. So at first, there doesn't appear to be a shortcut for computation. However, notice that 0, 7 is a linear combination of two eigenvectors, 2, 5 and -2, 2. In fact, it's the sum of them. So a to the 50th can be applied very easily to both parts in the sum. This means that a to the 50th times 0, 7 is a to the 50th times the sum of 2, 5 and -2, 2, which, by linearity, is just the matrix a to the 50th acting on each piece of the sum. The first part is 6 to the 50th times 2, 5, which we saw before. And the second part is -1 to the 50th times -2, 2. And this shows, in fact, that the sum is a vector with first component 2 times 6 to the 50th -2, and the second component is 5 times 6 to the 50th plus 2. Notice that the same kind of computation can be carried out with any other vector besides 0, 7. And that's because the eigenvectors -2, 2 and 2, 5 form a basis of R2. So any other vector can be written as a linear combination of those vectors. And then linearity can be used to perform a to the 50th on both pieces separately. Do you see what we've just done? We've made our understanding of the linear transformation easier by changing the description of 0, 7 in the standard basis to a description in another basis, a basis of eigenvectors. In this case, 0, 7 is 1 times the eigenvector 2, 5 plus 1 times the eigenvector -2, 2. This change of basis to something more convenient basically helped us see the action of A more easily as just stretching and or flipping along the new basis vectors. Once we determine how the basis vectors behave, we know where everything else goes as well. The basis of eigenvectors is hidden structure that is now revealed, and it turns out to be a better basis than the standard basis to try to understand what's going on with the matrix A. We won't always be able to find a basis of eigenvectors for any matrix A. In the next lecture, we'll try to understand and explore conditions under which we do have a basis of eigenvectors.